to the cloud.
Okay, so shall we start? Is it fine, or should I wait more?
Let's go ahead.
Sorry?
I said
Okay.
you should go ahead and start.
Okay, so, okay,
oh, wait,
okay.
Raja just got here. Hey, Raja.
Perfect. So we're just starting. Okay. So my name is Jan Drchal, and I'm from Czech Technical University. And I am a member of Artificial Intelligence Center, where I do mostly machine learning applications. So I did things in transportation, in robotics, and in like past 2 years or a little bit more, I'm working with natural language. So I do natural language processing. And actually, one of the tasks we were dealing with is not only the natural language processing, but processing logs, like log files. And we got some support from Marcel, from Red Hat via Marcel. And there were several master theses, and there are some bachelor students working on this right now. And what I'd like to show you is some, I guess, interesting things which we achieved. And I will be mostly talking about the results of these 2 guys who defended their thesis in summer, actually, while there were 4 theses, but all of this deals with the anomaly detection from log files. So the task is that you get your feed of logs and you try to somehow find whether there is some abnormal behavior. So Martin Peťák here, he basically focused on different methods of anomaly detection and applied them to log files. And Prokop was working on, basically, our approach is close to natural language processing. So we, unlike most researchers these days, I guess, we basically deal with the logs as with a free-form text. So it's, I will show you what's the difference in detail, but Prokop was really trying to employ the state-of-the-art methods which are used currently, like for 1 or 2 years these days, like BERT models. Well, you will see. So parse log files. So this is an actual example of log files of a data set which we were working with. This is based on Hadoop, and it's got quite fixed, I'd say, form. Nevertheless, you've seen some log files, definitely. And if you want to process it by methods of machine learning, then what's typically done is that it's parsed. So you typically parse it like to these two sets of information. So you have, we call it log key, or it's basically a template which you use in printf statement. So this might be one the extracted key or log key of single log line. So you can see these question marks here are for some parameters to fit in, and these might be whatever numbers, IP addresses, file names, and I guess you know. And these are the actual parameters which were extracted. So in most cases, current and whether it's anomaly detection, whatever analysis by means of machine learning, will use some kind of parser like IBM Brain. And okay, I see that I'm losing connection. Is my connection back? Because I had a message that it was frozen. Can you hear me?
We
Mostly hearing you. It's a little patchy at times.
Yeah,
well,
can hear.
okay.
And we currently are seeing the parsing log file, and your mouse seems to be
Okay.
visible.
Maybe. Okay, I'll try to switch to another Wi-Fi. Just wait a moment. Okay, can you hear me now? Is it better?
So far, so good.
Okay, now it should be better. Okay, so typically you would parse files like this, and then you will process, in most cases, actually, the only thing which is processed are these keys here, and mostly these parameters are just thrown away, at least for the anomaly detection, which we focus on. So these classic methods use, you need somehow to encode this data so you can process it with neural networks, decision trees, or whatever algorithm you choose to work with. And in most cases, these classic methods will extract these keys. As you can see here, this is extracted, these are extracted keys from a certain time window of log files. And then you will do something which we call the bag of words, which is a very simple thing. You just count the occurrences of log lines having specific log key. So you can see that there were like 8 of these received blocks, some kind of block of size meter from, so you basically convert a time window of logs to such a bag of words vector of integers, and then you use it. Obviously, you throw away the parameters, so you're losing probably or most likely some important information in this process. So our approach is actually work with the with logs as with text, as with a natural language. Okay, so definitely when dealing with machine learning, we need to have some data sets. So it's very easy to get any log files. It's not that problematic, but in order to estimate how our methods work, to assess, the quality of the methods involved, we basically need at least some labeled data, which means in case of anomalies, that it would be great to have a part of data where you have examples of such anomalies. So some domain expert, in this case, I guess administrator of cluster, for example, should somehow produce these labels, which is really not cheap. So having these constraints, we used several data sets. There is this site, you have a link to it, which is called LogHub, which collects such data sets which can be used for machine learning. And there are basically 4, maybe a little bit more, but there were 4 data sets which were at least somehow reasonable for what we wanted to do. So the first one is this HDFS, which I've already shown you, which is highly specific, I would say, but still this Hadoop distributed file system log, and it has basically 2 parts. So we have like 1.6 gigs of labeled data. So there are really the anomalies labeled. And then there's quite a lot of like 16 gigs of unlabeled data, which we can still use for learning, but at least for evaluation of how this anomaly detection works, it's needed to have some labeled data. So the nice thing here is that in this case, we have the annotations per so-called blocks. They call it blocks, and you can see it like maybe the time window. So you have basically a set of logs, and then there is a label whether it's resembles anomaly or not. So like 0, 1. Then there are 3 other commonly used data sets. So one is this Blue Gene. Then there are some logs from Thunderbird client, and also an OpenStack data. Well, all these 3 are commonly used, and you see them in papers on log anomaly detection quite a lot. But the problem here is that they are annotated in quite different way, a way which we didn't like. So in this case, it's like that every log line is assigned a label. So we thought that the task would be more interesting if we can detect anomalies based on the full like on many log lines, you know. So we can search for like complex interdependencies of what's happening in clusters, mainly because many of these, I guess, with the exception of Thunderbird, are based on cluster logs. So these things were quite less interesting. Second, the labeling in these is did based on some expert rules, which are, well, basically it's a rule-based labeling. So it's not like that there was a person looking at those log files and telling this is anomalous, this is normal. No, it's just there's some kind of rules, and it actually boiled down when we analyze these data sets that these rules were quite simple. So whether if there was something like error or warning on this line, then it was quite often considered to be anomalous, which is something we don't really consider to be anomaly. This is just an error or warning message, you know. So this is kind of what I want to tell you by this is that for this research, the greatest problem, I guess, is not availability of methods, but it's availability of data which are at least partially labeled. So what I'll be talking, basically, I'll be talking just about the results on this data set, which is the only one which has those interesting properties that the anomalies are manually labeled, and they basically reflect some more complex, more abstract things which are happening on the cluster, not just simple single lines. So just some statistics on this data set, because it's really, it's also not the greatest, which I can definitely imagine better data. So this is just the part which is labeled. So it's this 1.6 gigs. And well, there is some info on what length of what was the duration of data collection and so on. We have like 11 million log lines. And this is the thing which I found the most problematic, and it's that there are quite few types of logs, which turned out is kind of, well, this allows the simple methods to work quite well. You know, there are, it's like there are only 48 types of log lines in this. So we had to deal with it somehow. And of course, the important part is how many, and so basically we have these 11 million log lines, which are split into these blocks, which you can imagine as being the like some time windows on those log files. And there are roughly 3% of these blocks which are marked to be anomalous. So the rest is normal. So this is a typical setting that you have much less anomalies than there are normal samples. So the data looks like this, and what we do, actually what we did initially, and it turned out that it works the best, because it's like one step from that simplest way how to encode the logs. I've shown you that bag of words. We used this thing called word embeddings. You might have heard about that. And it's just about that you basically split the text of the log lines to words, and then you assign a vector which is describing each of these words. And these vectors are pre-trained on some large data sets. Actually, in our case, we've used that large unlabeled part of the data set, which was 16 gigabytes or so, to get these so-called embeddings. And these embeddings their size might differ, but in our case, it was like 300 values. So for each word, you get like 300 numbers. So we use this method, which is called fast text, which is based on another older method, word2vec, and fast text is something that was developed in Facebook research quite some time ago. So this is not like the total state of the art, but it seemed to be like the best, still simple approach on actually encoding the semantics of text of the logs, because this is actually the important part of what we think is of our approach, because if you encode just various log lines by the log key or template IDs, and in case of this dataset, these were like just only 48 of those, then you completely lose the semantic information on what's written actually in the text. But using these word embeddings, you can get numerical representation. So the embedding, as we call it, of each word in these sentences, and then you can aggregate them. So typically you do something like mean, elementalized mean. This, but there are other methods also. So we use this fast text. By the way, this kind of embeddings, when you use it on natural language, I'm not quite sure whether you've seen this. Probably some of you did, because these are quite known figures. But these embeddings have quite nice properties when you train them on natural language. So it turns out that then each word is represented in this multidimensional or high dimensional space, and for simplicity, this is just projected to 3 dimensions. So you can see if you find an embedding of man and embedding of woman, in this case, it's like that embedding is just 3 dimensions, so it's really simplified, and you find a vector which connects them, and then you find an embedding of king, then it turns out that often if you add the same vector, you shift this king, and that's possibly high dimensional space by the same vector, then you get at least close to embedding of queen. This is quite interesting, and there can be, just by training on large corpora of text, you can find embeddings which work in this way, and that you can basically use very simple vector arithmetics to get these relationships between, and these semantic relationships between data. So we did this, but we were not training it on a corpus of English text. We used the actual unlabeled part of the data for this. So this was just an example. So you get hopefully you understand more what this does. Okay, so then the next thing is when we are able to somehow numerically represent the log lines to actually find anomalies, to detect anomalies. Anomaly is, from our point of view, something which probabilistically is improbable, I would say. So we're searching for outliers of data, but it's not that simple in case of log lines, because logs have this time structure. There are sequences of logs. What's important, not just single log lines. So we basically try to encode these sequences, not single log lines, not single log lines, and then use methods which can deal with these sequences of log lines. And there are plenty of methods of anomaly detection. We tested quite a lot of them. And it turns out that, at least for this task and our data, we had the significantly best solution was to use something called AutoEncoders. And AutoEncoder is a machine learning model which is quite often used not only for anomaly detection, and it works quite simple. It's like you put something on its input, you process it by this model, this may be neural network, for example, and then you get output, which has the same form as the input, and you train this model in order to convert your inputs to outputs and have these as close as possible. So you basically, what we can achieve by doing this, if we feed this autoencoder the sequence of log files, we get another sequence at the output, and we train the whole thing. So the sequence at the output is same as the input. And obviously, one can say it's easy to train identity. So I mean, this identity function, but the architecture of these autoencoders is fixed in a way that there is the most, I guess, okay, so this is like the most common architecture where there is so-called bottleneck inside. So it works like that you take this quite high dimensional input here, and you use this part of network to convert it to much less dimension. So you basically compress the information. So compress information on this time window of log files. And then this decoder does exactly the opposite. So it uncompresses. And this is not definitely the lossless compression. So it turns out that you basically need to train something which can give you nice description. There's enough information in this low dimensional space, so you can extract it back to the original. And the idea how to use this for anomaly detection is quite simple, because you train it on normal data, and then, or in the case of log anomaly detection, it's like that you have normal data and you have just very few anomalies, which we can treat as noise, basically. So you can treat it on a training data, and you end up with output of this autoencoder and compare it to your target, which is same as what was put on the input. And you can easily compute any kind of error, like mean squared error or something like that. And this is called a reconstruction error. So you check your reconstruction error, and if it's low, if it's reasonably low, so you need to have some kind of threshold. So if it's low, you can say, okay, the reconstruction went well. So it seems like this network was trained to this probability distribution of this kind of input, and it's okay, it fits. Otherwise, if this reconstruction error is large, then you can say, okay, this might be anomaly. Yeah, so so you basically train it on this normal data, or normal data with just few anomalies, which are typically filtered out by the training. And then when you apply it for completely new data, which wasn't seen during the training, then you need to have a way how to set this threshold, which is done using some special part of the data set. And if you have this threshold, then you can really decide, this is okay, no, this is anomaly. So our approach dealt with these, mainly with these autoencoders, and we tested quite a lot of these. It turned out, finally, this is kind of results, and basically there are several measures we used to compare these models, and it's like this precision and recall and their combination. So we have single numbers, so this is like weighted mean of this geometric mean, harmonic mean, but it doesn't matter. The precision, so it tells you, if we say that something is an anomaly. So this gives our like the ratio of those which were actual anomalies in the labeled part of the data. We do this evaluation on the test set, which is built from this labeled data. And the recall basically tells us the proportion of how many of actual anomalies we were able to find. And this is just the combination of these two. So we did quite some experiments on this. The AE stands for the autoencoder. And this is quite interesting. This is that back and forth approach when you basically throw away all those parameters. And you see that still this went out best. So it's like, you can read it as like 88% of accuracy. We use this F1 score. That's because there are very few anomalies, and the most blocks of the data set are normal. So let's say this accuracy of this model is the highest. Still, these were the methods which were, I mean, at least this isolation trees and the below were the previous methods. So we were able to improve it by selecting the appropriate or improving the architecture of these autoencoders by, I guess, serious margin. But this second method here is, I think, it's the new thing. So it uses those word embeddings, which are in turn translated for the whole log lines to log embeddings, and then this autoencoder, which is based, the CNN here is for the convolutional neural network, but that's not that important. So it's like one-dimensional convolution here used, and this very method just takes these time windows, and you can see that the results are very close, but this method based on the word embeddings has quite a significant advantage over this like classic approach, and it's that it can deal with completely new log messages which appear. And I think it's quite a common thing. So while the BOW approach needs to have an information on all types or all those templates of the log lines prior to training, and then when you use it and you are limited just to those, obviously you can do something like creating like specialized type of message which covers all messages which were not found in the training data, but this does not work that well. So this actually, as it works on a word level, not on the like full logline level, this can deal with new messages much better, and the score, the accuracy is very similar. So this is the comparison of these methods, and the other student followed up, and he tested like more state-of-the-art ways how to, and in this case it's about encoding the whole sentence, the whole log line, sorry, to a vector of numbers. And in this case, it's based on different types of embeddings, which are called the contextual embeddings. And while in the previous, that word-to-vec or fast text basically compute these embeddings separately for each word which you have in the log line, and then simply summing, computing mean out of these vectors, you get a single vector describing the whole log message. In this case, we use these BERT models, which if you just search for BERT models, there will be plenty of links you find on Google or Google Scholar. And in this case, you get basically for each word, or to be more precise, we are working on slightly lower granularity than on the word granularity. We work with so-called tokens. And basically, you can see this is an input to this model. And if there is a word which happens to be common in some training data, then it's typically represented by a single token with this ID. However, the word like rumination here, which is not that common, was split to two parts. Yeah, so it's kind of subword level, which is now heavily used. And there are some special types of tokens. There is a token which marks the start of the sentence, or logline in our case, and other token which marks the end of it. So the thing here is that if you have, for example, the word visually here, then it will get some representation at the output of the network. But this representation is influenced also by other tokens in the input. So it's really contextual, you know. So this is quite large difference in comparison to these older word representations. So you have this. This is an example of DistilBERT, which is just one of many types of these BERT models. And this is just a huge, really very, very large neural network. And by the way, if you want a representation of a whole input sentence or logline, it's typically extracted from this part, which corresponds to this like start token here. So there are other possibilities, but this is what is typically used. So for example, in our case, we use this kind of model, and for each log line here, we were able to extract, and it's given by the architecture of the network, 768 values, you know, floating point values. So this vector is extracted from here. Just a small information on how these so-called language models are trained. It works quite simply, and it's very effective, because you don't need to have actually any labeled data to pre-train these models. So basically, what is done, you get a huge corpus of texts. And this, in case of natural language, this might be like Wikipedia, and we often used Amazon, how is it called, Common Crawl, which basically samples internet every 2 weeks or every 3 weeks. So this corpus which you use for training is typically something in tens of gigs, or even larger, hundreds or terabytes of data, the newest models. And you learn it very specific tasks. So it basically learns how language works. And there are many tasks, but the most, I think, the original tasks and those which are most widely used are these. There's a masked language model. So basically, it works as this. You select a random sentence from your corpus. Then you mask, so you use a special type of token for that. Random token here, so it's this token which corresponds to the improvisation. And then you push it through the network. And the network should give you an answer, and you train it. So it maximizes, so it gives you basically the predictions of what this missing word should be. And you train it, so there's maximized, so you maximize the probability that the original word. So it's the right input for this network, you know. So by this you train it to fill in words just by their context in the sentence, by the surrounding words. So this is the next language model, and then there are other types of these approaches. So it's like you put 2 sentences, and it's often combined with the masking actually, but you can put 2 sentences from source text, and then you basically try to find out or train the network whether the second sentence was the following sentence in the original text, if it really followed this first sentence A. So by training for these tasks, you can learn something which has quite how to say it, which covers the probability distribution of natural language. So we did very similar thing as you see here, but we did for logs. And obviously we used once again the unlabeled part, that 16 gigabytes of logs of HDFS. So so it was quite a lot of data to do this. Actually, we used some slightly different approach to those tools, which is called the inverse causa task, but it's not that important. We did it like it's I guess quite straightforward. So we have these log lines. We just split them to chunks, which were those time windows, and then we use these time windows to basically find whether the log line from this this chunk appears to be in that chunk really in reality, or whether another whether it comes from different chunk of data. So this is how we trained whether a certain log line fits into the context of other log lines. So this is what worked best. However, this approach turned out to be inferior to the previous one, and well, it was quite slight. So if you compare to the previous method, which used the simpler word-based approach, I mean the fast text, which got this F1 like 85%, with this Distilbert and this special type of the network, we get to something like 79%. And well, we found that this problem is caused by the data, because as I said in the beginning, this HDFS set is quite limited in type of log file. So it's like probably too complex method for simple data. So we have this machinery which is these days widely used to translate language to language and so on. But it's like there were only 48 sentences to translate. And of course, there are the parameters, the part of the log lines, these might differ, but there are like 48 types of messages in this case. So I guess this method might work well, but not on this data. So it's well, it's not the worst result for this method, but it really can't shine, at least now. So
I have a question.
Okay. Should I put it back?
Yeah, so just some high level questions. One is, you had this is on HDFS, right? You had all the logs enabled? Like are there different logging levels? Just my own clarity.
Sorry,
are there like different logging levels that could be enabled in HDFS? And did you have all the logs enabled and you only saw 48 keys?
Oh, sorry, I can't. I can't understand you. There's some problem with audio.
Is this any better?
It's better, yeah.
Did you
some systems have like different logging levels, right? So like info, debug, right?
I mean, log levels. If you
Yeah. So you had all the log levels turned on for this. And you still only saw 48 keys.
I don't think so that in this HDFS data that there were no log levels. It's a little bit atypical type of data. Yeah. But I think it's okay. Sorry.
And the other question is something that comes up is like, if it's like, I understand if it's like, if this were applied to like Kubernetes or something, where like that might directly go to like the administrators or like the DevOps folks who are responsible for managing the cluster, and they're the only people who are looking at it. But like for things like, there are definitely like a class of applications like HDFS, where like the people who see the error messages, right, are not the people who put those error messages in the first place, or the log messages. And so they tend to be very difficult to interpret by people using the system. And so is there something on top of this that you need to like add?
Yeah, actually it's on the next slide.
Oh, okay.
If you need, I understand. If you get just the information, this is anomaly, look at that. Okay, this might be important information. But what you can do with this is to use various methods of method explanation. So you can basically find out what log lines were important in the decision. It's whether it's anomaly or it's normal. And this is visualized here. So this is an example of a part actually of a block, which was in this case, this block was marked as anomalous, if I'm not wrong. And you can see that there are this background color here, which is computed per log line, tells you that, for example, these lines here were important for the actual outcome of telling, okay, this block is anomaly. Yeah, so you can ignore these because, well, these would otherwise move the model in direction of the normal normal classification. But if the total outcome was anomalous, then it's probably a good thing to look at these orange log lines. The problem is, well, I don't know anything about about this kind of data set. It was just the only we were able to use, you know. So it's, yeah, it's definitely not typical data set, I guess. At least I've seen also other logs from clusters, which is, I guess, the most interesting part for you. Yeah, but we had to deal what was available actually. So yeah, but you can do it, and there are several methods which can be used to extract this. So you can basically do the root cause analysis when you have this. So this can direct you. So yeah, and actually, what you can do, this is an example from the first thesis which was published a year before, actually. So this is quite simplistic, but it already uses the fast text. You can do projections for each log to like 2 or 3 dimensions, so you can actually see them, and then you can typically find clusters of logs. In this case, these are a point represents a single log line, but basically you can, in theory, we haven't tested it, but it works like that for natural languages. You can use this, for example, these representations, which so you can read numbers from the autoencoder from its bottleneck part here, and you can project it to 2 dimensions once again, because this is basically what this gives you is an embedding of a whole time window. Similarly, you can take these embeddings or similar embeddings where you put a whole sequence of log files here. So that might be more interesting, and I guess, than this simple example where we just projected single log lines. You can do something similar, and you can project like the sequences of log lines. So each of these sequences will be single point here, and you can then, if they form clusters, then you can see, okay, this behaved very similar to this one, which is close by, while sample from here will be something completely different. Something different is happening on a cluster. So maybe such kind of visualizations might be also interesting. And then there was another kind of application we used to these embeddings. These were actually, once again, the BERT embeddings. We got these were data from Škoda Auto, which manufactures cars in Czech Republic. And the task was not anomaly detection, but they wanted to detect certain, okay, from time to time, there appeared a log line which contained an information on the length of manufacturing process. And the task was to predict this value as soon as possible before it actually happens, so they know if something is not getting overloaded. So these are other possible applications of these methods. So not just the log anomalies, but if there is, for example, a specific log line having some value to that, we can train the model which will predict this value prior it actually appears. So, and or the other thing is a classification. You can classify things based on logs. So, of course, in this case, you need to have these training data. So, in that case of manufacturing process, this time information was inherently in the data. It was there, but you can probably come up also with other tasks where it's not in there, and you need to use some other source of data for that. So yeah, this is basically it. So just to conclude, I happily showed you how it's typically done if you want to make this machine learning approach to detect anomalies in log files, and that we chose another way. So while this back and forth approach is the approach which throws away the parameters, we tested this fast text, which works on word level and which works at this data, which, as I said, these are not really nice because there are only 48 types of logs. So these methods are kind of limited to what I guess they would otherwise achieve, but still, this is like comparable result, and it gives you the ability to work with new log lines, so new log messages which were not seen during the training. Then there is possibility of these like state-of-the-art methods with these contextual embeddings, which once again, this would, I guess, work better, much better when there are more types of messages. And then there is definitely possibility of explanation. So that's it. And well, basically, the most pain for us is really data, because as you've seen, we have like one reasonable data set, which is definitely not enough to compare various methods and to find whether something is in general better than something else. So it would be really nice probably if you know, and if you have access to data which can be somehow labeled. And the thing is that we're really not interested, and I think the users of such systems would not be interested in something which just tells you, okay, there are too many error messages, something's probably happening, but the labeling should be done on like a higher abstract level. So it should be inferable from whole time windows of logs that there's something which does not correspond to the normal state of the system. Yeah. Okay, so that's it. If you have any questions, please ask. Oh.
I know that Raja probably had questions, but I regret he had to drop.
Ah, okay. Okay, so Marcel wrote that he's also okay. I'm not quite sure whether should I explain something more, because I deal with machine learning and I'm not quite sure what is your background. Happily, it was reasonably explained.
I can ask maybe one thing. You can hear me
Mhm.
clearly, right? So you mentioned that Lime, I know, like they are basically feature-based explainability methods. They can be used. They can be used to explain some of the root causes behind anomalies. Are you aware of any work, or like, let's say not just work, but any other idea that we can that can point us to root causes of those anomalies, or like sometimes failures, using the log, not just like explaining the machine learning model, but just using the raw data to explain those root causes? You know what I mean?
I'm not quite sure. You mean because we were using like the raw data. This is the raw data, so okay, you mean like explanation, like okay, something which will tell you something like text explanation or something like that.
Yes.
You mean like higher level explanation, not just pointers.
Exactly. Not just pointers to examples, that leads to that classification result like Lime provides, but like a more high level explanation that system admins or users can understand.
This would be totally great, but I guess you really need to have some data, some training data for these explanations. So otherwise, these systems learn from examples. Machine learning is based on that you have some training data and you use examples to train these networks. So if there was some kind of database of anomalies with explanations, and the problem might be it should be quite a large one, I guess, then it would be possible. Other possibility might be and this will be definitely less general, if you come up with some kind of classification of various types of anomalies. But it kind of defies the thing, because the anomaly is typically something which never happened, or these are the types of anomalies, I guess, people are most interested in. Yeah, but in that case, if you have this classification and you have, once again, some examples where the anomalies were classified, then this would be possible. Probably other way to help in the root cause analysis, some thinking about it might be maybe visualizations like this, because if you ever ended up with anomaly, you can similarly project it, and you can project your past anomalies, and then if a new anomaly comes, then you can probably project it and see if it's close, for example, to some older anomaly. This might work like without any training data, but it's
Yeah,
it's,
that could be
yeah,
one approach, I guess.
that could be one.
Yeah,
of-
but
Mhm.
again, I think when you encounter with a, let's say, unknown data point, and if it is an anomaly, it might be novel anomaly too. So, you know, I think, but if it fits, or if it's basically like if you are gonna do some sort of a distance-based method, and if it fits the existing clusters, I mean, you can still say, hey, that looks like that anomaly that I've previously observed in the past. So that's also one idea. I see your point. But yeah,
and
I mean,
then
that domain is.
Mhm.
Yeah, lack of labeled data overall. I know what you feel, what you're getting at. That would be great if we would have some sort of a, you know,
If there was possibility to
collection of-
collect such data, which means, for example, administrators will be able to give some like more complex feedback on what they're doing, you know, and but
yeah,
this
you're right.
is very hard, I guess. Yeah.
Yeah, thank you so much.
Mhm. Okay. Okay, so any other questions?
Other questions?
You're not getting any sound, Michael. I can see you trying to talk, but
Oh, can you hear me now?
oh, now I can. Yes.
Oh, okay.
Cool.
I hear
I
you.
was asking essentially, are there other questions? So it sounds like one of the pain points that you have is sort of a similar one to the things we're running into all the time, which are just the difficulty of getting access to the data. Is that right?
Yeah, definitely.
Okay. I asked primarily just to validate what I think I already knew. One of the things that we are working on now is ways to actually start to capture more of the data from the various clouds that we're involved in and make it available through data use agreements and things like that. So I'll make sure that we keep you in mind as soon as that's available.
Yeah, I was talking with Marcel about this, and he pointed me to one of your projects. So, well, we're just, I'm not quite sure who will be responsible for that, but these people will send me some data, but these will be unlabeled. So, but I still will get some idea on how logs of your clusters look like, so we can at least build some solutions to visualize those data, like these images I've shown here, maybe more involved images, which will basically visualize whole sequences of logs at once, which is, I think, more interesting. So maybe it won't be possible to use it for anomaly detection. Well, basically it can be used for anomaly detection, but we won't know how good it is. So yeah, because basically you don't need label data for anomaly detection, but you need at least some data to evaluate the system to know if it's not just randomly selecting the logs. So
yeah, so part of what we're hoping to do is come up with ways that allow a little bit more labeling. That some of this ties into, I mean, as you guys know really well, some of this ties into GDPR and figuring out how to thread a path through GDPR.
Do you think it's possible to have some kind of this data collection in administration interfaces, like implemented inside? So
I'm not sure if I
those,
understood the question. Sorry.
I mean, if it's possible to have some kind of data collection in administration interfaces of clusters, or like, you know, solutions which are based on Red Hat software. I understand it's impossible to have something like this on clusters of other institutions or your customers, but I mean on your own clusters which you administer.
So the goal is to do just that. The difficulty is that So let me back up. And rather than do this now, only because it's 10:30 and I'm supposed to be in a different meeting.
Sorry. So
Let's do a follow-up, or maybe make that as a topic either for the next one or the one after, at which point we hopefully will actually have some sample agreements for people to look at and help us think through whether they work. And I am going to quickly add that to my to-do list so that I don't forget. Telemetry working group, discuss data. It's going to be gated mostly on what we're able to get through various companies. We're in the middle of having discussions with Red Hat and to try and identify experts at Red Hat, expertise about GDPR to help us think through how to actually make those logs available.
Okay, perfect.
Telemetry working group. And I guess I'm giving that to me.
You can add it to the discussion with Raja and Marcel for about 2 weeks from now, Michael.
Yep.
Yeah.
That's
Or I'll reach them. So it's fine.
Cool.
So
Thank you, Jan. This was fantastic.
Okay.
It was really good.
So thank you very much, Jenny. I will send you the slides. If you
Thank
want.
you. Yeah, and we'll post a video on the telemetry working group, and we'll send an email out.
Okay.
And it's okay to give your contact information in there for anybody who has any questions. I know you're on the mailing list, but
Yeah, just write anyone. Please write me. It's in the slides, and I'll just send it from my academic address. So
awesome. Thank you so much.
okay. Thank you too.
Thanks,
and
everybody.
have a nice day.
Take
Bye
care.
bye.
You too. Bye bye.